Welcome back. Welcome back to 823 class. In this class, we have treated the first module that has 3 units. We have treated introduction to algorithm. We had looked at how basic algorithm could be matched to form advanced algorithm. We had also looked at how to evaluate performance of algorithm. And that was how we ended module 1. And then we came to module 2 last week. We looked at one of the approaches of implementing algorithm called divide and conquer. From the divide and conquer, we all looked at merge sorts together. I gave you an assignment to look at quick sorts and compare quick sort and merge sorts. And hopefully I'm going to upload the link for you to upload that assignment on the portal after the end of this module, hopefully. Today, we're going to continue on sorting algorithm. This time around, we want to look at another approach to sorting algorithm. So today we'll be looking at heap sort algorithm. I hope everyone can see my slide where we stopped. Can you see my slide? Can you see my slide? Okay, yes, thank you, Destiny. So we look at heap sort algorithm. So what does heap means? From the African perspective, when you say heap, it could be a tuber of yam. You know, when you harvest yam, you put everything that looks like a heap. And for those of us that are a bit lazy in terms of laundry, when you don't like washing every now and then, you pile the dirty clothes and you pile it and keep piling it until the time comes and then you want to go for laundry. You put everything, you stack it down on the floor like an heap of clothes. So it's the same thing with heap sort algorithm. So what does heap sort algorithm mean? Heap sort is a kind of special binary tree algorithm whereby we create something that looks heap-like. And then within the heap, we heapify. Heapify means that we sort within the heap. And then as we are sorting, we are popping the sorted data into a fresh array until the number is sorted. And you know, of course, when you're sorting, you're sorting from minimum to maximum, like 0, 1, 2, 3, 4, 5, 6, like that. Or you're sorting from maximum to minimum, maybe 1 million, then 99999, then 889 till you get to 0. So that's why we have minimum heap or maximum heap, depending on whether you're sorting ascending order or descending order. Let me even draw what an heap look like. For those of us, maybe some of us, we've never done laundry before, or we've not had any reason to see anything that looks like an heap. So an heap would look like this. If you can see my screen, something like this. This is how an heap looks like. So when you have an heap, is something like this. It could be heap of yam tuber or cloth or whatever. This is an heap. Can you see the screen? Can you see this? I tried to put a diagram on the screen. Okay, thank you. I just wanted us to be on the same page. Thank you. So let's proceed. So like I said, heap sort algorithm, when you have a binary tree and then within the tree you sort, then wherever you have sorted, you pop it out. Let me also draw so that you see what I'm trying to say. So you will see this tree. Within this tree, you're going to be sorting the nearest node to one another. Can you see what I'm drawing? Yeah, you need to sort, yes, the data and the nearest node to one another. And then anyone, depending if you have a minimum heap or maximum heap, it's still the same thing. It's just whether you have a ascending order sorting or descending order. You see this is 1, 4, 1, 3, 4, whatever is minimum. So from minimum down to the maximum. This is maximum heap. The first element is the maximum, and then it goes to the minima. So we call it max heap. So the highest one here, you pop it out and put it, you have like a list or an array, depending on the way it's implemented. So when you get the first one that is the minimum, you place it here. And then the next one that follows, you place it here. And then the next one that follows, you place it here. It looks rough. Let me withdraw it before I give you example. Don't worry, I'll give you example how it works. I don't just like dumping algorithm on students. I want you to see how it works so that when you now see the algorithm, oh, this is how what she was explaining looks like. This is clearer now. So what I'm saying is that there's going to be like in the memory where you want to store the arranged set of numbers. So when you sort the first sorting, the maximum here, you bring it here. And then you amplify again. The maximum that comes up, you bring it here. And then you amplify again. The maximum that comes up, you put it here. And by the time you get to the end, you already have something that will look like maybe 10, 7, 5, and maybe 3, 2, 1, 0. Now let's go through an example together so you understand how an if sort algorithm works. So the first is to create an heap of the unsorted data. So when I say create an heap, you want to create something that will look like this of the unsorted data. So how do we create it? We want to create a binary tree and put the unsorted data. The binary tree is a tree that has only 2 nodes. So when you open a node, if this is a node, whatever that can come out of it cannot be more than 2. And then this one, whatever will come out of this cannot be more than 2. So we call it binary tree. Whatever comes out of this cannot be more than 2. Whatever comes out of this cannot be more than 2. And then you continue until the entire data you are trying to sort has been represented like a heap. So let's assume that the data has finished now. You see what you have already looks like an heap. So that's the first thing the algorithm wants to do. It wants to create an heap of the sorted data. Then a sorted array is created by repeatedly removing the largest or the smallest, whether you are doing maximum heap or minimum heap, whether ascending or descending order, by removing the largest or the smallest element from the heap and inserting it into the array, just like I showed you earlier. So the heap is constructed after each removal. How does that work? Okay, so I don't scare you with the algorithm here. Let me explain how this works for you with an example. Let me take a plain. I'm looking for a here. I think this is a bit plain. So give me an unsorted list of number, and then we create the heap, and then I'll show you how it works. Okay? How the algorithm works. I don't believe in cramming algorithm. I believe in understanding it. So when you have this diagram, I'm trying to use it to store some numbers. So, okay, give me some numbers. Somebody on mute. You guys should drop some numbers, random numbers that we need to sort. Quickly, please.
3.
3, okay. Okay.
7.
7. Why are you trying to use the one I gave? Just give me, you can give me higher numbers. Don't worry. You can even give me minus. Okay,
9.
go ahead. 9.
17.
Okay. 17, awesome.
27.
27.
23.
Are they all odd numbers now? You guys don't like anything to be evil.
16.
16. Okay.
Then 8.
8. Thank you. Don't mind this, my 8 one. Okay, so should we do a maximum or a minimum? Should we go from lowest to highest or highest to lowest? Anyone? I'm at your service. So while you're thinking about that, the first thing in the algorithm is to create an heap of these numbers that you have put here. So you have how many numbers? 1, 2, 3, 4, 5, 6, 7, 8. So you have 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. So this is an heap of the 8 numbers. So I'll put all of them there. These 3. It's not easy to write with a mouse, so please accept my handwriting as I'm writing those numbers. 9, 17, 27, 23. Shall I draw it more fatter? 16, then 8. So the first thing on the algorithm is you create something that looks like an heap. Okay? You can go on and on and on and go down, 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 depending on the number of the data you're trying to sort. So for now, we have 8. Now, the next question is, are we sorting at ascending or descending order? Descending order. So descending order means that the last number at the end of the whatever is the smallest. So the first thing we now do is we look at what you have created, this EP you have created. Should I make it fatter? Do we even have space? Hold on. Can we get 8 with this my fat diagram? 7, 9. I hope everyone can see my screen.
Yes, ma'am.
Okay. 9, 17, 27, 23, 16, and then 8. So we now have where we want to push the sorted lists. So the first thing you want to check, we want to epify to make sure that it's the largest one that is here, and then we'll push it out. So if we look at the first number here, 17 and 8. You need to be, I want us to be on the same page. Hold on. So when you compare these two, 17 and 8, 17 is still the highest, so we'll leave it. When you compare 17 and 7, 17 is higher than 7, so you swap. You bring 17 here, you bring 7 here. And then the next thing, you also want to compare 17 and 27. 27 is higher than 17, so you bring 27 up here, and then you put 17 here. To continue here, you need to come to the other side of the tree. 9 and 23. 23 is higher, right? So what do we do? Let me be sure that you're listening. We swap. We have 23 here. We have 9 here. Here we have 16 and 23. Which one is higher? 23. Do we swap or we leave it? We leave it because 23 is higher. Then we come to this node, this side of the node. 3 and 27. Which one is higher? 27. So remove 3, we put 27. So you have 27, you have 3. 27 and 3, you come to this side. 27 and 3. 27 is higher than 23. So we leave 27. So we are done. If you find the highest, when you look at it now, the highest is here at the top. This is the highest. So what do? We bring the highest here, 27, and remove it from the heap. And then we'll do the same EPFI again and pop the highest. We do the same EPFI again and pop the until the entire array is sorted. So let me try 2 more times, and then I'll allow any one of you to try 1 more time, and then at least we'll have almost gotten to the end of the array. Is that okay? So if I want to try again, and I say, I come to this side, 8 and 7, because 8 is higher than 7, I swap it. This gives me 7, 8 goes up. Okay. I come to this side of the heap, 8 and 3. 8 is still higher than 3. So I have 8 here. I have 3 here. Then I check 8 and 17. I'm also going to swap. I'm going to bring 17 up here. 17. Then I have 8. And then I come to the other side here. 23 and 9. 23 is higher than 9, so this is perfect. 23 and 16. 23 is higher than 16. This is perfect. So I come to this final leg. Between 17 and 23, which one is the highest? 23. So push 23 here. When you want to pop this, you bring the highest here as well. So you have like 16 here. And this node disappears. Since the highest is at the top now, 23, what do? We move it here, pop it. 23. Yeah. And then if I go back again, 7 and 3, 3 is smaller than 7. You realize that for every time it epifies, it's actually sorting even it's basically sorting the heap too. So it's not only about popping, it's also sorting the heap. When I get here, I'm looking at 17 and 7. 17 is higher, it remains. 17 and 8, 17 is higher, it remains. I come to this side, 16 and 9, 16 is higher, it remains. Then I check 17 and 16. Meanwhile, we had popped this off. So I check 17 and 16. 17 is the highest. I bring it up here. Creating a vacant here. Within this vacant, 7 and 8, 8 is higher. So 8 comes up. Seven moves to that side. So you have 8, 7, and 3. 7 and 3. And what do? We bring about 17 here. I'll remove it from here. And then you do the next one. Who want to try the next one? What do you think will be the next number that will go up? Destiny, yes, 16. Awesome. 16 is going up. So you move this 9 up here. And then you pop your 16 here. When you pop this 16, what's the next number that is going? 9. Is Destiny the only one in this class? 9, Okon, okay. I'm actually looking at my chart too. So we'll pop the 9. So what's the next number? 8. Yes, this is the next number, 8. And then when you pop the 8, you have your 7 and 3. Sorted. This is already sorted. So we started by following the algorithm that says, now let's go back to it now. It should be more easier now than me telling you to just cram it. So the first is to create the heap of the unsorted lists. You can see now. Then a sorted array is created by repeatedly removing the largest or the smallest elements from the heap. Now it's making sense. And inserting it into the array. The heap is reconstructed after each removal. Now you see. So you have two things working. You have the one that build the heap, okay, and you have the one that heapify. This is like max heap. You can have minimum heap, you can have maximum heap. But like the example we did maximum heap is the same thing. So while that is building it, the other one is swapping in between the heap. I wanted to ask, I think I've already written it here. I wanted to ask, what's the complexity of heap sorts? But the answer is already written. Next class, I will remove this from my slide. So basically, because it's a binary tree, the data that is meant to stream like in serial form, we break it into binary. That's where the log n is coming from. And then as we epify in n steps, that's where we have n log n. Insertion sort is not that bad. For those that have entered or those that have sold with all this mama in the market, or you have entered public buses, you see the conductors, they do insertion sorts every day, every seconds. So they'll put an unsorted, they'll collect the money from the passengers, unsorted, and then they will just take one of the money, like take the 500, look through all those things, see where they put more 500, they will insert it there. They take another money, 200, see where they insert, see where 200 are, take another 1,000, take that one to the back end, to the end. That's insertion sort. And for those that are used to the library, I don't think anyone goes to the library anymore to take physical books. What the librarian basically does after you have poured the books on the table, we are so lazy. We take the book, we use it, we drop it on the table, take the book, drop it on the table. When you are gone, they look at the book serial number and take it to the bookshelf and look at exactly where the serial number matches that book. That's insertion sort. Oh, I wanted to show you how this also works. I showed you how match sort works last week. A visual of the algorithm. Do you know why insertion sort best case scenario is n? Does anybody know why? So if you are inserting according to the algorithm, you have to, if this is, I'm using the money as an example. If this money is let's say 500 naira, and I have a bunch of nairas, I want to insert. The best case scenarios is when the entire naira is already arranged. So once I just go through, if these are where 500 starts from, I'll just insert it here. So I'll insert the money here. And because I only go once, this is N. But in real life, you won't get a sorted, if you are using insertion, in most cases, you really get a sorted list of data. In most cases, you get randomized data, which means that you have to go through N in N time to insert this one. Then you pick another one, you go again, you insert it, pick another one, you go again, you insert it, pick another one, you go again, you insert it, and then you have it in a quadratic form. So at times, you know why I keep showing the worst case, best case scenario? Because in as much as for your class, all you need to understand is the worst case, what will have happened. But in reality of life, at times, your algorithm might perform better based on the nature of data that is being given to you. So you really cannot just sit and say, oh, because the worst case scenario of insertion sort is n squared. But if the data you are dealing with is a sorted data, that for every time you just need to pick one data that is missing and put it there, just once, then you wouldn't say that because it's n squared, I don't need it. Okay, if it's sorted, then the best case, I pick the data, and by the time I go in one direction, I put it there and the array is already sorted. I know that in several classes, whenever they see this theta and theta log n, they just freeze out. Like, and that is why I'm taking my time to explain this time complexity beyond. I hope I'm still audible. Beyond this class, it will go a long way in whatever you do as a computing expert. So as I was explaining, when it comes to choosing an algorithm, a lot of things goes into it. You want to look at, I've explained this all over and all over. I explained this in module 3 of unit 1 as well, when I was explaining that there's so many things you want to consider when it comes to you choosing an algorithm. A lot of things go into it. Whether you're using space complexity, time complexity, correctness of the algorithm, even the design of the algorithm, implementation. Oh, I don't want divide and conquer. Fine, this will reduce the complexity from n squared to L log n or log n. Okay, can I do reduce and conquer? Or can I do, there are several approaches of algorithm. For the sake of this class, we had to limit you to these basic examples, but there are loads and loads of algorithm designs. So in this last second unit of module 2, you learned about the importance and classification of certain algorithm approach and techniques. So let's now look at, I've been talking about sorting in terms of algorithm design techniques. Let's look at search too. How do you look at algorithm design techniques in terms of searching algorithm? Pardon? Am I still audible?
Yes, ma'am, we can hear you.
Okay, I'm back. So let's look at searching and then look at a sample algorithm techniques. For the sake of this class, we're only going to look at basic search, and then we'll look at algorithm design, and then we'll look at time complexity too. And when I talk about search, search is something we do every day. Whether you're searching your phone on Google or you're searching a contact, you're looking for somebody you saved, and you don't even know what you used to save the person's name, but you shall know you have the person's contact. These are all searching. Even at home, you do a lot of searching all the time. And even within your memory, you do a lot of searching. For every time you're trying to recollect a memory and events, what you're just doing is searching your brain. So in computing, searching is so fundamental that you hardly see a complete application that does not have an embedded searching algorithm in it. So we'll look at one of the basic fundamentals of searching algorithm in computing. Today we're going to be looking at linear search and binary search. What does linear really means? Linear means something that just goes straight one way. Da, 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 da. This is linear. And then binary is like you have seen example in the divide and conquer. You've seen example in the heap sort. Binary is something that you keep dividing. You didn't just go like this, you divided it, and then you divided this, and then you divided this, and then you go on and divide. That's binary. So that gives you overview of what linear search is. Linear search is searching linearly, boom, 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 and so on. Binary is you dividing and dividing and dividing until you get what you're looking for. So if I have like I told you, I don't like reading slides. I just like explaining. It's easier. You can always go and read your slide yourself than me reading the slides to you. So if I have maybe 10, 2, 7, 9, 30, 5, 0, 4. So what linear search will do is linear search will come to the first element. Maybe I'm looking for 5, Abby. Linear search will come to the first element and check, is this number 5? No, it's not 5, it's 10. No. Go to the next door. It comes there. Is this one 5? No, it's not. Oh. Go to the next door. It comes there. Is this 5? Bow. Go to the next door. And the linear search will continue until 5 is found. And then returns 5 as output. So if it searches like that, what do you think the time complexity will be? Are there people in my class?
Yes.
What's time complexity? I already showed you the slide, so
Is 0 interim?
are you
Yeah.
reading my slide for me? Yeah,
Yes.
the time complexity is n, the total number of data sets. So that's the worst case scenario. You know why it's the worst case scenario? It's the worst case scenario in the sense that if you have a set of data and the number you are looking for is at the end data. If the number you're looking for is at the end, maybe this is 0 to n. N could be 1 billion or 1 trillion of data sets. The worst case scenario means that I have gone through each of these one by one, one by one, one by one. The number I was looking for is actually at the end. So how many times will you go to get the number? End time. So if n is 1 trillion, 1 trillion times to get the end. That's the worst case scenario. The best case scenario is if the first number you pop out, that's actually the number you're looking for. But does not normally happen like that. That's the best case scenario. That the first cell I checked, that's the number. But the worst case is that is what we are always interested in anyway. The worst case scenario is I checked and checked and checked, and the number is the last number. That's end time. And that is why you have O of n or T of n, whichever way you want to write it. So don't cram it, please. In reality, advanced computing hardly uses linear algorithm for searching, except if the data is few unsorted data. But when you have data that no few, there are several other advanced search algorithms that does searching better than linear. Because you can imagine if your system will have to sort one after the other until it gets to trillions of data sets. I don't know, and you need to do that all over every time. You wouldn't want to use that kind of algorithm. However, we use it for data sets that are not that many, especially when they are random data sets. They are not sorted. And binary on the other hand, of course, when you hear the word binary, I know the first thing that should first of all come to your mind is the time complexity is going to be in log form because now you are dividing, right? It's critical that you can see my screen. I hope everyone can see it. So if I have, yeah, if I have 4, 9, 12, 24, 32, 50, 71, 94 in a data set, and somebody tells me, go and look for 9. I'm looking for 9. So what will binary do? Binary, first of all, splits this into 2 equal half. It's looking for 9, Abby. It will check. Is 9 greater than this number or less than this number, whichever one? 9 is less than both of them. But which one is smaller? This 24. So binary will discard this entire side of the data. Okay? And then it will come here. Out of these 4 that we have, it will divide this into another 2 equal half. It will come and check is 9 here. Between this one and this one, is 9 there? Yes, 9 is found. But imagine if 9 is not found. But now we also look at which one is greater than 9, 12, or this one. The left one is greater than 9. We discard this place and then divide this into 2. And then check these 2 boxes. Which one is 9? And it goes like that, continue to divide. Did you notice that this example I gave you for binary search, the numbers are sorted? Did anybody notice? Type or say yes. Am I still audible? Hello?
Yes, we can hear you.
Yeah, did you notice that? Okay, Ahmed, thank you. Did you notice that the number are sorted? Imagine if the number was not sorted and I'm using binary search, how long will it take me to get, if I use the random example I gave during the linear search, how soon do you think I'll get where I'm going to? All this Turenchi is just everything I've explained.
I think n/2. Am I correct? N log
Yeah.
n, kind of.
Even if you do n/2, if it's random, you keep jumping here and there. Now you jump to the left, and then you see the left side is lesser, and then you get to another point, you see it's higher. Okay, let me give you an example. I wanted to justify why we don't use binary search for unsorted lists. It cannot work. It worked easily because the numbers were sorted. It was easy to compare the content of the right side or the left side. If the number is not sorted, maybe I have 0, I have 13, I have this is still sorted. I have 2, I have 17, I got 5, I got 3, I got 1, I got 50. So if it's not sorted, if I divide this, maybe I'm actually looking for 1 or 0, depend. When I divide this and then I check, my mind is going to be like, okay, which one is higher? 17, maybe I'm looking for 50. If I divide it and I check what is here and what is here, where do you think the search will first of all tilt towards? Is it going to tilt towards the right or the left?
The right.
The right.
Why will it go to the right? I'm looking for 50. This is the number we are looking for. Of course, you go to the left. If you say 17 is higher than 5,
Oh.
so 50 is probably going to be on the left side. You will say that, okay, if 17 is greater than 5 and I'm looking for 50, which is more, so it means that 50 is probably going to be on the left. And it will come here. By the time you slice
That's the
it,
question.
you have a question.
Is it
Please ask
possible?
the
Is there any
next
way
one.
is
There
there
any
a way
way
the
to what?
algorithm is there any way the algorithm would know that is handling a sorted array or unsorted?
That is what I'm saying. You know, for your level, you are not meant to be taught anything about heuristics, as in whereby you put some basic information within the algorithm for the algorithm to be a bit more intelligent in terms of searching. For your level, the algorithm is blind. It cannot know whether the data is sorted or not. So an algorithm does not know whether the data is sorted or not. And the way binary search works is that after dividing, it will compare the number it's looking for with both right and the left. If the number it's looking for is higher than what is on the left, it believes that the number is on the right. If the number it's looking for is lower than the one on the left, means the number is on the left. The algorithm is trying to look for the closest number to what it's looking for. If you remember, I'm even glad I didn't just show you the algorithm and start reading the algorithm to you, you don't understand it. See, this is how binary search works. If I have 1, 2, 3, 4, 5, 6, 7, 8. Okay, and I tell the binary search, please look for number 8 for me. He doesn't know where number 8 is. He doesn't know what kind of data is. He doesn't know the structure of the data is there. The first thing we just do is to come here, divide it by 2. Okay? If it cannot be divided equally by 2, do n plus 1 divided by 2. Just look for middle number. And it's looking for 8. This is the 8 is looking for. So the algorithm will pop what is here, what is in this memory and this memory. So if after popping what is on the left memory, it sees 4. 4 is less than 8. It pops out what is on the right memory. It sees 5 at this midpoint. So the algorithm will assume that, 5 is more than 4, and I'm looking for 8. It means that my 8 is going to be around this side. So what does it do? It leaves this entire point and come to this side and divide by 2 here. And when you divide by 2, it brings this 8 here. And check, what is here? 6. What is here? 7. So I don't need this left side because my 8 is greater than 6. So I'm going to the right side. My 8 is going to be around this side. So discard all this place too. I hope you can see. And then it comes here. Pam. It's the last one. It's looking for 8. And finally, here is 8. So you see, it's easier because the numbers are sorted. But imagine if number is not sorted. The algorithm will still get the results. But after jumping around, jump to this side, jump to this side, jump to this side, jump to this side, and finally it will get the response, unlike if it is sorted. And that is why when we're talking about binary search, you would only see a non-entity that will try to use binary search to solve a searching problem of a random number that is not sorted. For people that have attended this class or any computing experts, nobody would use binary search to search random data sets. It's fast because it keeps by 2. Instead of going on like the linear where it's be going one after the other, binary is faster because by the time I divide this one and I discard all of this, I've cut the time by half and I move to this side. And when I'm on this side, I divide this by 2 too. I discard all of this. I've also cut the time by half. So that is why you have the log n instead of n. So by now, you should be able to compare the difference between binary and linear. In fact, make it an assignment. The comparison between binary and linear search, I'll put it on the portal for you to upload. So in this unit, you have learned about the importance of searching and 2 important searching algorithms. This brings us to the end of this module. So in the next module, you'll be taught some useful data structure for writing algorithms that are required for solving real life problems more efficiently. Do we have questions?
Okay, yes, ma. Good evening.
Okay,
Hello, ma.
Daramola Oluwatobi, your hands are up. Please speak up.
Okay, good evening, ma'am.
Yeah, good
My
evening.
question is regarding the binary.
Where's my camera? I want you to be able to see me.
If we say that the time complexity for binary search is log n, and we know that it will not work, or let me say it's not effective when the data is unsorted. Now, what if maybe for instance, now I want to design a system and I'm to use binary search. Then I know that, okay, I'm going to sort this data first before I implement binary search.
Awesome.
By the time I put together the time complexity now for both the sorting and the binary search now, let's assume it's n log n. So does that not imply that I might have to maybe opt for another algorithm for implementing searching instead of me sorting first and then doing the binary search? At the end of the day, the time complexity might possibly not be favorable compared to another algorithm that won't have to divide it. So that is the kind of question I'm asking. What do we do in such a case?
Damola,
Have to stop.
I'm so excited at your question. You're already thinking like a computer scientist. Do you know the secrets in life? We don't really normally have sorted data. And in life, most of the problem you'll be facing, you don't really get sorted data. So what most computing expert does is the best of the best of sorting algorithm, of searching algorithm, we embed a sorting algorithm function. Do you understand? And that was why one of the classes we had to look at basic and advanced algorithm. So at times to sort some data set, to search a data set in some algorithm, you might need to sort them before you search them. And there's some algorithm whereby you don't really need to sort them to search them. You just hash it and then meaning you make everyone unique and then search through them depending on the algorithm you want to make use of. But in real life, we hardly get sorted data. Somebody somehow had used a certain algorithm to sort that data before you start searching it. But if you want to implement, like you rightly said, that was why in module 1, Unit 3, when I was teaching time complexity, you will see I was showing you T1, T2, T3, that at times in your implementation, where you are trying to search, for example, if your case is a searching algorithm, you want to implement some basic algorithms to make your searching easier for you. And your time complexity is the average time it takes one of those algorithms to end. If you attended that unit, I did explain to you as well. So it all depends on you playing around with your skill of algorithm evaluation. When you have tasks to do, now you're an expert to look at, okay, should I just use linear? Using linear will give me end time. Okay, what if I'm combining a certain algorithm that has log n plus another log n of this binary? Do you understand? It will still give me a log n at the end of the day, and that is still faster than me using linear. So you now start playing around with you combining 2-3 algorithms and then looking at the time complexity that really works for you. I'm glad you already started thinking of applications. Awesome. That's awesome. Next person.
Thank you.
You're most welcome. Okay, so nobody's hand is up. I'm assuming we understood very well. I'm assuming we will go to the portal to fetch the assignments. I'm assuming we will all try to attempt the assignments. And I'm also going to add one more practical, which is beyond you looking at the application, also try to test some of those algorithms. Testing them is easy, and I can even get you some code, just put it there and run it. can see how the number you put there is being sorted. And you can also go to ChatGPT and get a lot of some codes that shows that you have this random number is sorted in a way that works depending on what I state in the assignment. But I want you to have a practical grip of the course too, and to make it easier for those that are not dev or those that hate anything programming. I only had one practical to the assignments. You can see you already have 3 assignments there. You have one of your algorithm. You have the second one of quick sort and match sorts. You have the other one of linear and binary. And I am going to have a hands-on practical where you would look for maybe I'll think of the ones that will be easier. Maybe match sorts, quick sort, whichever one. I'll put it on the portal. You run it and you send the code and the output and evidence that shows that you run it. Okay. And having said that, we come to the end of module 1 and 2. Hopefully, Professor Azeta will take this class next week, same time. Thank you for attending the class, and I wish you the very best.